Şimdi yanılmadığımı anlatıyorsun sen birkaç dersi. Doğru düzgün bir soru olmayacak. Ama bu en başta bir x'a'ya göre integral aldık ya. Sonra bir pattern görmeye çalıştınız. O pattern'da da aslında x'a ile bağlantılı bir n tanımlıyoruz. O zaman ben şey anlamıyorum mesela. Niye biz xi plus 1 üzerinden bir integral almak zorunda kalalım ki? Demek ki xi dedim, yani oradaki i derecesi içeride bir n'le bağıntılı. O zaman biz ilk integrale, ilk forma bir x yazmayı unutmuşuz ya da yazılsa aslında tek bir integral içerisinde tüm değişimi görebiliriz.
Okay, so this is my problem. Okay, I have to evaluate all those integrals, n minus one of them, n minus two of them. So, and eventually I will take the limit as n goes to 0. So I have to evaluate them one by one, all of them. So that's basically what I'm doing. I'm just picking up one of those integrals, and I'm evaluating it. And this is the result.
Ama bu integrallerin hepsi birbiriyle bağıntılı ki. Biz aradaki bağıntıyı bilebiliriz. Onun hepsini normal hesaplamasını görelim.
Why?
Üzerine de görelim.
How are they related?
O kısmını unutmamız. O kısmını
Yeah, that's the basically the relation I mean, you see, the integration variables, the x2, x3, x4, etc., they are all independent of each other. They are not related with each other. So I have independent integrals. Now, on the other hand, what I'm integrating is some kind of an exponent. Now, if you look at it, the S is the action connecting, basically, to be more precise, it's basically the Lagrangian connecting the two time intervals, two successive time intervals. So that is why S depends, Ti minus 1 depends only on these successive two positions. I don't know if I'm answering your question, but so if when I evaluate xi integral, just it's an arbitrary one of those integrals, one of those many integrals. The end result is basically a similar integrand. Again, but still I have to evaluate I'm evaluating over xi, I have to evaluate over xi plus 1, xi plus 2, xi plus 3, xi minus 1, etc. I have to evaluate over all of them. Or if you want, you can just think of this as I have to integrate over x2, just put I is equal to 2 over here. So this is the result of the x2. If you put I is equal to 2, it's the result of x2 integral. Then I have to evaluate x3 integral, x4 integral, x5 integral. But now, in the first case, I just seem to see a pattern. When I evaluate, you see, the pattern is that here, this square is just the differences of the two positions, just one after and one before. The difference squared. It will. I'm claiming that it will always be so. And then I have this factor 2 over here. Is nothing but the number of integrals plus that I evaluated plus 1. So that's kind of my claim. So I'm just saying that, okay, so let me just assume that I evaluate everything until the xi integral. I evaluate x2, x3, x4. Well, let me just put it, okay. So I evaluate everything from x1, x2 up to xi. The result is this one over here. And then I'm evaluating the xi plus 1. Now the term that contains the xi plus 1 is this one, this additional term. And then I see the pattern that my suspect is correct. And hence, let's say this pattern is, since I know what the general pattern is, I just write down the result when I evaluate all of those integrals. And there I have, well, each integration brings such a factor. I have n minus 2 integrals. And then they also bring such factors over here. And then this here I have the n minus 2 plus 1, which is n minus 1. And hence this, and also this is the difference between the the position 1 before and the position 1 after, all squared. Now, the different integrals, they are not really related with each other. But I just see the pattern, and hence I can say what the result will be after I evaluate an arbitrary number of integrations. I probably didn't answer your question, but...
Yani ben çok sayıda olan integrenin scientific bir özelliği varmış da önceki bir integrenin içerisine koyabilmişim diye düşünüyorum.
Okay. So all those integration variables are independent of each other. Now, this is just an alternative way of treating the quantum mechanical problem. Now let's start a slightly different subject. Eventually, we will be going to electromagnetic interactions. Well, if you remember from your electromagnetics courses, the electric field, you can write it as minus the gradient of some scalar potential in electrostatics. And this scalar potential was kind of, you can shift it by an arbitrary constant because the position derivative will basically will not be changed. So phi goes to phi plus, let's say, lambda t, even it can be a time-dependent quantity, will still give me the same electric field. Or let's start with, let's just take lambda 0. I shift the potential by lambda 0. Now, what is the Hamiltonian of my system? Well, I can write the Hamiltonian of my system as p squared over 2m plus phi, or it can be p squared over 2m plus phi plus lambda 0. Now the question is, I have two different Hamiltonians. I have to solve two different differential equations, but they should still correspond to the same thing. And furthermore, since the physics shouldn't change if I just use phi or phi plus lambda 0, any expectation values, let's say the expectation value of position, the expectation value of momentum, etc., should be the same. Now the question, let me just use the tilde notation for the shifted quantities. So let's say I have one solution of the initial Hamiltonian. Well, I should have a corresponding solution. Now let me use the ket notation for the shifted solution problem. And of course, somehow, since the expectation values will all be similar, I should have some relation between this psi tilde should be related to this psi ket by some kind of a unitary transformation. And then the question is, what is U? Now, it should be unitary because psi tilde should be 1, just like psi psi. The probability, the norm should be conserved. So this tells me basically that U should be unitary. And what else do I know? I want x to be the same whether I evaluate it in psi or psi tilde. So this tells me that x should be equal to U dagger x U. So this U should also be commute with basically x, the position. That is one thing I expect. Well, you see, it need not commute with the Hamiltonian though, because they can have different energy eigenvalues. And in fact, what we expect is that E tilde to be just E plus lambda 0. This is what we would expect. And in fact, this u is, we can just write the u is nothing but e to power minus I over, well, let me write it in this way. Let me assume that psi tilde at t equal to 0 is equal to psi at t equal to 0. Well, my initial condition, I can just impose the same initial condition for both of them. So psi tilde at the time t will be just e to the power minus I over h bar h times t psi tilde at t equal to 0. Now, this is h tilde minus I over h bar ht e to power minus I over h bar lambda 0 t, basically because h tilde is h plus lambda 0. Well, psi tilde at t equal to 0 is just psi at t equal to 0. So psi tilde t is nothing but psi of t. Well, this is true, in fact, for any ket, not necessarily an energy eigenket. Now, if psi t and psi tilde t are energy eigenkets, psi of t is nothing but e to power minus I over h bar e of t, psi 0. So psi tilde of t is e to power minus I over h bar e plus lambda 0, psi of t equal to 0. Here I have psi tilde of t equal to 0. Well, this is basically something we expect, because if you shift the potential, the energy of the state is also shifted. The energy is being the kinetic energy plus the potential energy. So we see that E tilde is actually E plus lambda 0. Not a great surprise here. Now we can also straight away see this relation from the wave functions and using the propagator. You see, we already know that psi tilde of r of t is nothing but d cubed r prime r t r prime t0, or let's just take t0 to be 0, psi tilde of r prime 0 d cubed r prime 0 of psi of R0. Well, let me put a tilde on top of this one also. Basically, this is the propagator in the presence of the shifted potential. Well, we already know that this RT, R prime 0, in terms of the path integral, L tilde, but keep in mind L tilde is just T minus phi, kinetic energy minus the potential energy. This is T minus phi plus lambda 0. This is the Lagrangian, unshifted Lagrangian plus lambda 0, minus lambda 0. So this propagator is the sum over paths of e to power I over h bar dt L. This is the ordinary Lagrangian, non-unshifted Lagrangian, minus I over h bar dt of lambda 0. This is shifted, the propagator under the shifted potential. So the propagator under this shifted potential is, you see, lambda 0 is independent of my path. It can be a constant. In fact, here we see that it can even be some function of time only, as long as it is independent of the path I am considering. I can just take out that lambda 0 term out of my path integration, because path integration is just the sum over paths And since all of those paths has the same factor in the sum, so I can just factor out that common factor. What remains is nothing but my unshifted propagator. So if we go back to our wave function, so basically what we are doing is I'm assuming that I have the same wave function initially, but then they evolve under different potentials, but the difference in the potentials is just a shift. So this is equal to minus I over h bar dt lambda 0 d cubed r prime r of t r prime 0 psi of r prime 0. But this is the wave function at the time t if the potential was not shifted. So in a sense, okay, on one hand, we know from classical physics that the shift in the potential shouldn't make any difference, shouldn't have any observable differences, consequences. Now we see that it changes the wave function slightly. The wave functions, the phase of the wave function changes differently if the potential is slightly different. Well, if this is an overall change in the potential, again, it won't have any consequences. So you just shift the potential everywhere, so all the wave functions, all the components of the wave function, whatever component you can imagine, their time evolution will acquire this additional phase. So this will be an overall phase of my wave function, and an overall phase, I don't really care. It's only the phase differences that will be important for us. Now this phase, so although the overall phase is not really important, this allows us, it makes a difference when we are talking about several different phase shifts, different potential, well, not phase shifts, but let's say potential. If there is potential differences, we can measure that potential difference using this phase shift. So this is basically the idea. Just take a very long conducting cylinder and create a potential difference. Take another very long cylinder, again conducting. So imagine you create some wave packets over here. Identical, oh, sorry. Okay. So you create your wave packets over here. And you send your wave packets either from the top or from the bottom. For example, you can arrange that the potential difference is 0 until your wave packet enters the cylinders, and it is non-zero. Okay, so the potential difference might be 0 until the wave packet enters, so that there is no force acting on my system. There is no potential. But when my system enters the cylinder, I turn on the potential. But you see, the potential inside the cylinder, if it's very long, will be 0. The potential will be constant. There will be some finite potential difference, but nevertheless, the potential will be constant inside the cylinder because there won't be any electric field inside the cylinder, inside the conducting cylinder. So there won't be any force acting on my particle at all. My particle will not be feeling any force. Classically speaking, well, nothing should change. But you see, what happens is, the wave packet that goes through the upper cylinder acquires one phase that is proportional to the potential over there, and the wave packet that goes through the lower cylinder acquires a different phase, which is proportional to the potential over there. So there will be a potential difference. So if you somehow make these packets interfere at the other end, so here you have a screen, then you have an interference pattern, well, this interference pattern on the other side will shift depending on whether you have exerted a potential, you created a potential difference or not. There will be a shift in the potential, in the interference pattern. Mainly because the packets that went through both of those cylinders, they acquired a different phase. Again, I repeat, classically, there is no force acting on the particle. I can just arrange my setup so that no force will be exerted on my particle, classically. So there shouldn't be any effect. But quantum mechanically, we will see this shift in the interference pattern, although there was no force acting on my particle. And that shift in the interference pattern is a measurable consequence of this potential difference. Although classically there shouldn't be any difference, quantum mechanically there should be some difference. You see, the wave function acquires a shift based on the potential. Now you can consider the wave packet going from the top. It will acquire an additional phase due to the potential inside the cylinder. The wave packet going through the lower cylinder will acquire a phase proportional to the potential in the lower cylinder. And since we are creating a potential difference between the upper cylinder and the lower cylinder, those two wave packets will acquire different phases if there is a potential difference. So the interference pattern is basically determined by the phase differences between the wave packets. Now, applying a potential difference in the cylinders will change the phase difference, and hence it will change the interference pattern. The interference pattern will basically shift. And in fact, this is quite similar to the Michelson-Morley experiment. The idea in the Michelson-Morley experiment was they were sending light rays into different directions, and if the light had a different speed depending on the velocity of Earth in ether, then the phase difference between those two light rays would shift depending on the velocity of the ether. So you should observe a shift in the interference pattern and hence detect the ether wind. They never detected it. Well, this is a similar setup, similar in the sense that you have that interference pattern, and any applied potential difference in this case creates a phase shift. And that potential difference, since it contributes to the phase difference between those two packets, will acquire different phases. Now, you can see it also using the path integral formalism. You see, let's just look at this one. Let's say the final position at the time t final, the initial position at the time t initial. This will be a sum over paths of I over h bar s. Let's say s, okay. Now, I can divide my paths into two different classes of paths. the paths that go through the above cylinder e to the power I over h bar s above plus the paths that go below through the below cylinder. But you see, S above is nothing but, assuming there is no other potential in the system, dt t minus phi above. This is S0 minus phi above, T final minus T initial. And then I have S below is basically the same thing, S0 minus phi below times T final minus T initial. So this propagator is basically the amplitude that we go from the initial position to the final position through paths that go through the above cylinder with zero potential multiplied with e to the power minus I over h bar T final minus T initial phi above, the potential inside the above cylinder, plus the amplitude or the propagator, or the probability amplitude that my particle goes from the initial point to the final point through the below cylinder, multiplied by e to the power minus I over h bar T final minus T initial times phi below. This will be equal to, well, let's say A1, some amplitude plus some other amplitude times e to the power minus I over h bar T final minus T initial phi below minus phi above. All of this thing multiplied with e to the power minus I over h bar T final minus T initial phi above. Well, that overall factor doesn't really make any difference, because when we are talking about probabilities, it will be basically the absolute value of this. So that overall phase, this one, is just an overall phase, will not change the amplitude that my particle goes from xi to xf. But you see this phase over here, which is proportional to the potential difference, will change the amplitude or the probability. So that's basically why that we will get this shift. So this is basically one way of measuring the potential differences, if you wish. But again, the crucial thing is I can just arrange the time dependence of this phi, of the potential, such that there is no potential difference until my particle enters the tubes. And there will be this potential difference only after my particles enter the tube, which means that classically my particles will not be feeling any force whatsoever. And hence, classically, there shouldn't be any consequence of this switching on and off the potential, but quantum mechanically, there will still be observable consequences due to this different phase shift of the different components of my wave. You see, on one hand, I have the electric field. Classically speaking, my particle never feels an electric field. Nevertheless, there is observable consequences. This will be also the case when we study the Aharonov-Bohm effect. Okay, we will come to that later on. Now, another thing about this, that the phase shift creating observable consequences. You see, let's consider gravity. Gravity is one of the problems, one of the most important problems that we are trying to solve nowadays. We don't have a theory of gravity. There's no quantum theory of gravity, to be more precise. Now, one of the problems that we are facing in trying to solve quantum gravity is basically this phase shift. So you see, if you look at Newton's gravity, we have if you look at the equations of motion or the Lagrangian, 1 over 2 m v squared minus, let's say, mgz close to Earth. Well, you see, S is just integral of the Lagrangian over time. So delta S is equal to 0, just means the delta of the variation of 1 over 2 v squared minus gz dt should be equal to 0. Well, the mass just disappears everywhere. So the mass basically doesn't play any role in the trajectory of my particle, or the way my particle behaves under the gravitational force. So we say that, okay, this is one of the reasons why we say that, okay, the gravity is a geometrical effect. It doesn't really related with the particles, the mass of the particles moving in a gravitational field, but rather it is an effect that is determined by the geometry of space. It doesn't really depend on the particle moving in my gravitational field. The consequences of gravity is independent of its mass. But let's see what happens in quantum mechanics. Yes, if you put your particle in a gravitational field, our Hamiltonian will be p squared over 2m plus mgz. Now let me just imagine these two cases. I create my particles over here and somehow send them over there. I can send them through a path, such a path. You start from A, go to B, and then go to C. Or you start from A, go to some other point D, and then go to C. And then you try to see, okay, what will be the phases that each one of these particles acquire as it goes from A to C through these two different paths. Well, you see, as they go from A to D or B to C, they will acquire the same phase because they are going through the same potential change. But the phase that the particle acquires as it goes from A to B is different than the phase that it acquires as it goes from D to C. And this phase difference is proportional to the mass. So if you calculate the phase difference, well, I will not go into the details. Let me just quote the result. This phase difference just calculates it turns out to be m squared g L1, L2, lambda bar is the de Broglie wavelength divided by h bar squared. Times sine of delta. Now L1, L2 are basically the lengths over here. This is L1, this is L2. Sine of delta in the experimental setup, what they do is you can have this plane. So you start your particles from one point, you send it to some other point, and the plane that the particles move, you can just tilt it. And this tilt angle is what's called that delta over there. And then you just look at how they interfere at the point C. And the interference pattern, as you see, it changes as you change delta. Well, if you look at in the book, there is also the reference to the original article. This is what you see as you change delta. So since the phase difference changes as you change delta, the number of neutrons reaching your final point will oscillate. And this is what you see. And this is experimentally verified. But now the problem is, this depends on the mass of the particle. It's not really a geometrical effect. Or is it? We don't know. We don't really know. Maybe it's still a geometrical effect. Now let us look at one more example of this phase. Or no, let's not rush it. Now, any questions? Now, what I would like to discuss now is what is the Hamiltonian for particles that are moving in an electromagnetic field, and then describe the Aharonov-Bohm effect. Well, the short idea of the Aharonov-Bohm effect is the action for a particle that is moving in a, let's say, vector field, or the Lagrangian, is just T minus U, U being any kind of the potentials that you might have, minus E over C V dot A. So the action in the presence of this vector potential will be just the action in the absence of the vector potential minus E over C A dot V dt. But V dot dt is nothing but dl. So this is S A equal to 0 minus E over C A dot dl. Now we can basically do the thing that we had done right over here in this example. So I can imagine a region of space. Here B is non-zero. Out of it B is 0. For example, I can just imagine a very large solenoid where outside there won't be any magnetic field. Inside there will be some non-zero magnetic field. Well, outside the magnetic field is 0, nevertheless the vector potential need not be 0. Then if you just consider the amplitude for a particle to go from one point to the other point, it can go above this solenoid, but in this case it will acquire the phase A dot dl. Let's say from this is the point A, this is the point B, from the point A to the point B through above. If the particle goes below, then it will acquire the phase from A to B, A dot dl, but the integral should be below the solenoid. So these will be the two phases that my particle will acquire. Now we had already seen that the phase difference will change the interference pattern at the point B. So phase difference would be just from the point A to the B above, A dot dl, minus from the point A to the point B below, A dot dl. Well, I can just combine them, and it will just give me the integral of A dot dl around that closed path. So I just go from A to B above. Well, minus from A to B is nothing but plus from B to A, just change the order of integration. Instead of from going a to b, go from b to a in the second integral. It will change the sign. So I first go from a to b above and then from b to a below. I sum them up, but that is my loop integral. But any loop integral I can write as an area integral of the curl of that vector field by Stokes' theorem. Well, the curl of A is nothing but my magnetic field, which tells me that the phase difference is equal to B dot ds, which is the total magnetic flux. But you see, the magnetic flux is non-zero, because within my loop there is a region where the magnetic field is non-zero. Although my particle never feels a magnetic field, its properties is still influenced by the magnetic field over there. So then there's still the question. In classical electrodynamics, we always say that, okay, the potential and the vector potential are not physical quantities, the fundamental quantities are the electric field and magnetic fields. Well, here we see that even though my particle never feels an electric and a magnetic field, it changes. Its behavior is modified because there is a vector potential over here. Well, although it does feel the vector potential, you see, the problem is how much it is modified is still determined by the magnetic field. So you see, it depends, the phase difference depends only on the magnetic flux. So it's still the magnetic field that determines how much the wave function will be modified, even though my particle never feels that magnetic field. So it's not straightforward to say that, okay, the vector potential is fundamentally, I mean, we cannot really say that the vector potential is fundamental because still the changes are related with the magnetic field, not the vector potential. Anyway, we will discuss this in some more detail on Monday. Any questions? See you on Monday.